there, folks. The topic today, we're going to talk about composition of functions. So this is similar to what we did last time. Last time we talked about combining functions algebraically, and so in essence, you would take the equation for f of x and the equation for g of x, you would add them together, and that would be f plus g of x. Or you can do the same thing with subtracting, multiplying, and dividing to combine functions. What we're going to do is called composing functions, and rather than adding functions or subtracting functions, we're going to take the input, which is x, we're going to replace that with a function. So essentially, this is going to be functions of functions. To get things started, we're going to use a motivating problem. So it's got to do with Thanksgiving, and we can pretend it's Easter, I suppose. And a turkey for Thanksgiving costs $32.50 at the supermarket. But you have $5 off as a coupon, and the store's also having 20% off the discount. So the question becomes, what's the final price? Depending on what order you apply the coupons in, you could end up with a final price of $22, or you could end up with a final price of $21. So we don't really know which one of these is the actual price. I mean, if you've ever worked in a store, you probably know that they apply it in the order that gives them the least discount, but we'll pretend that that's not the case. If you recall from function notation, f of 3 simply means that we replace x with 3 in f of x. And so we can extend this further, and we can replace x with something other than just a number. We can use a symbol like this concerned face, and if that was the case, we would replace x with one of those concerned faces. If f of 2x plus 7 was what you were interested in, same strategy. We're going to replace x with 2x plus 7. In f of x. So really, it doesn't matter what we're inputting for x. We can replace it with a number, like 3. We can replace it with a letter, like A or B. We can replace it with a symbol, or we can replace it with an entire equation, like 2x plus 7. So instead of simply a number, we can substitute in another function. So composition of functions. F of g of x is how you write it, or you could have written g of f of x. Technically, this is formed when the equation of g of x replaces x in f of x. Another way of writing this is f o g of x, and technically that would be pronounced as f of g of x. So maybe we'll put that in brackets. F of g of x. And we've got this concerned face here. That's because there's something you've got to be careful about. And that's that f of g of x is not the same thing as f times g of x that we talked about yesterday. So the one on the left means you replace x with g of x. The one on the right means you take the entire function f and the entire function g and you multiply them. So a slight difference in notation, but it makes a big difference in how we handle the question. So we've got 3 functions. We've got f of x equals 4x. Let's highlight that one in yellow. We've got g of x equals x minus 2. We'll give that one a color. I don't know, let's go blue. And h of x equals x squared. Let's go with like a green of some sort. Okay. So we want to make some composite functions. F of g of x, we're going to start by just writing f of x, and it's 4x. But instead of an x, I'm going to leave brackets. And then where the x used to be, I'm going to write the inner function, which is g, which is x minus 2. To complete this, I'm going to have to actually go ahead and multiply 4 by x minus 2, and this will become 4x minus 8. Let's try another one, g of f of x. Start by writing g of x, which is x minus 2, but where x was, leave brackets. So bracket minus 2. And then where x used to be, we're going to write f of x, which is 4x. So this one will simplify to simply 4x minus 2. We can keep going. G of h of x. So g was x minus 2. So we'll go bracket minus 2. And then where x was, we'll write h of x, which is x squared. So this will become x squared minus 2. G of h of minus 2 is a little bit different than what we've seen before, because now we've got an input inside h of x. So I'm going to make g of h of x first, which we already did. It's equal to x squared minus 2. But then I'm going to replace x with negative 2. Negative 2 squared minus 2. This will be 4 minus 2, or just 2. Another option, if you've got a question like this, is you can just compute h of minus 2. You'd use h of x, x squared, put minus 2 into it. It'll turn into a number. You can then take that number and stick it into g, which was x minus 2, and you'll get the same answer. Maybe we'll do that. Maybe we'll do that here for the next question. So h of x, we write h of x, which is x squared. So it's bracket squared, and then we write h of x in the brackets, x squared squared, which is going to equal x to the power 4. For h of 2, we can find h of 2. H of x is x squared, so h of 2 is 2 squared, which is just 4. Which means we can now put 4 into our original function. H of 4 equals 4 squared, which is 16. We could have gone and plugged a 2 into h of x. 2 to the power 4 would also have given us 16. So it's just another strategy for solving these. Notice that f of g of x does not necessarily equal g of f of x. So it really depends on the order of the composition, what the actual equation is going to become. So now, when you are creating composite functions, you can substitute a value of x into the new formulas, or you can do arithmetic in 2 steps, and that's what I talked about with D and F, 2 different strategies for solving it. The order does matter. On your own, consider f of x equals root x minus 1 and g of x equals x squared. Let's find f of g and g of f. Okay. So f of g, we're going to start by writing f of x, but we're going to leave brackets where x was. So this is going to equal the square root of bracket minus 1. In those brackets, we're going to put g of x, which is x squared. So this is going to equal the square root of x squared minus 1. G of f of x, however, we're going to write g of x with a bracket for x. So this is bracket squared. And then in the brackets, we're going to put f, which is root x minus 1. So this is simply going to cancel our square root out. And this equals x minus 1. Notice how these are not the same. Square root of x minus 1 for g of f of g, and x minus 1 for g of f. So they're 2 different equations. Technically, we should be really careful because we had a square root here. We can't forget that it was there. So we need our restriction that x must be greater than or equal to 1. Otherwise, technically, this equation does not equal the line above. So now determine the domains of f of x and g of x and both composites. So maybe we'll split this up into 2, or maybe we'll just do it line by line. F of x was root x minus 1. So for f of x, we had a domain of x must be greater than or equal to 1. Because anything less than 1 creates a negative in our square root, which is not allowed. F of g, or maybe we'll just do g of x next. G of x. G of x was x squared. There's no real restrictions on what you're allowed to do with x here. So this is all real numbers. Now, f of g of x, the first one here, root x squared minus 1. Now, there's a couple things that can go wrong here. You could put a 1 in for x, or sorry, not a 1. You could put in like 0.5 in. Squaring it becomes 0.25, and you'll get a negative in the square root. But you can also put a negative in, and as long as that negative is between 0 and 1, like negative 0.5, you're going to run into the same issue. So, excuse me. So we have to kind of account for both positives and negatives. X can't be between 0 and 1, and it also can't be between 0 and negative 1. A clever way to write that is that the absolute value of x must be greater than or equal to 1. That means x can be 1, 2, 3, negative 1, negative 2, negative 3, but it can't be in that range of negative 1 to positive 1. You could have also solved this by just writing greater than positive 1 or less than negative 1. Lastly, g of f of x. It's x minus 1, but x is greater than or equal to 1, so our restriction is still that x is greater than or equal to 1. What about working backwards? If we're given that h of x is f of g of x, and we need to find f of x and g of x, this time we have to go from the full version, the composed function, back to the originals. So let's try a question. H of x equals x minus 2 squared plus x minus 2 plus 1. Now, oftentimes, you're going to see what I would describe as the outer function and the inner function. And when I'm talking about outer and inner, I'm talking about the function outside the brackets here and the function inside the brackets here. Whatever we label as g of x needs to appear wherever x was in f of x. Technically, there's a bunch of ways of doing this, but I'm going to show you a sort of a strategy that will make it a little bit easier for you. If you look for a pattern, if you look for something being repeated multiple times, in this case, we've got an x minus 2. That's a strong hint that that's your inner function. So if we were to use an inner function of x minus 2, so we could say g of x equals x minus 2, now these brackets become x in my outer function. The outer function is f, so we'll call it f of x. And I can call my brackets x now, x squared plus x plus 1. So now if I was to compose f of g of x, wherever x was, I would write x minus 2. And f of g of x equals h of x. Whoops, f of g of x equals h of x. Technically, you could be more creative if you want, but this is going to be the easier way to do it. Look for an outer, look for an inner. Question B. I think my inner function is going to be x cubed plus 1. G of x equals x cubed plus 1. Now I can replace it with x for my outer function. And I can say the outer function is root x. Let me give you an example of a way that you can do this that would be a little bit different, because these are all going to have many, many answers. What if instead I made my outer function, f of x, the square root of x plus 1? Now my inner function, g of x, needs to turn x into x cubed. So g of x could simply equal x cubed, and we would be done. So you got to be a bit creative here, but there are simple ways to do it, and I think many of you will end up with the same functions, but it is possible to get other functions. In the previous example, there may be an infinite number of possibilities. But we can usually find an example of an equation inside brackets. On your own. Ben is shopping for a turkey for Easter and knows 20% off or of a 20% off sale on Saturday. He has also has a $5 off coupon for the same store. Let X represent the current price of turkey, let D represent the price after a 20% discount, and C as the price after using the coupon. So we're going to create two functions to figure out what price is going to be for the turkey. C of D of X means that we are going to apply D of X first, the 20% off first, and then we're going to take $5 off of it. So C of D of X, C of D of X, we're going to take the 80% off, 0.8 X. That's 20% off of 100, leaves us with 80%. But then we're also going to subtract $5 from the price. So our equation would be 0.8x minus 5. Because of BEDMAS, we do the 80% first, then we subtract the 5. However, if we did it in the opposite order, so we took $5 off first, then took 80% off, that's equation D of C of X. We're just applying our operations in a different order. We would take $5 off first, so we would go X minus 5 first. The result of this gets multiplied by 80%. So the equations look different, but one of them is going to get us a lower price. The turkey is initially $32.50, which will give the lower sale price. Technically, we want to be taking 80% off of the largest value. So we want to be taking 80% off of the total price and then subtracting 5. If we did it in the other order, and we took 80% off of the price after $5 off, we're going to lose out on some of our savings. So that means C of D of X is going to be the winner. C of D of X is going to be 0.8 times 32.50 minus 5, which is going to be $21. At what price would the other option be better? Technically, if we wanted to solve for this, we would have to create a system and graph it. We would have to graph y1 equal to 0.8 x minus 5, and y2 equal to 0.8 x minus 5. And we would look for the graph that gives us a higher or a lower price. And sometimes what you will find is maybe one of them has a graph like this and one of them has a graph like this. And there's this point where they're equal. One of them then goes up in price, one of them then goes down in price. It turns out, though, that when you do graph this, they don't touch, and one of them is always better. So y2, C of D of X, is always going to be the better price. Now we consider a composition of two functions, f of x and g of x, but this case where the two functions are not explicitly defined. Not explicitly defined. So we don't know what the functions are. You'll be given either a graph or you'll be given a table of values, and then you have to work backwards. This is where we use that trick that I talked about on the first page of finding the inner function and using it as an input for the outer function. And I'll show you what I mean. So if we know that the function or what the functions are, we can find them ourselves and proceed as we did before. If we can't do this, then think of x and y as functions, y values as functions. We've got two graphs. We've got the blue one, f of x, and we've got the red one, g of x. Now, we're going to find a value of one function first, and then we're going to work up to finding composite functions. So f of minus 1. We want to trace the graph of f of x and figure out the y value when x is minus 1. Go to -1, trace it up, and we have a y value of 5. G of 0. Similarly, go to 0, go up to g of x, and figure out the y value. G of 0 is 2. Okay, so now we're going to use the fact that g of 0 is 2 to figure out what f of g of 0 is. In essence, because g of 0 is 2, this is like f of 2. We can now go to 2, trace it up to f, and we have a y value of 8. So let's try one that we don't know the inner function already, g of f of 0. We've got to find f of 0 first. So we go to 0, go up to f of x, and f of 0 is 8. So this is kind of like, whoops, not f of 8. This is like g of 8. We now go to 8, go up to g, and it looks to me like it is, like it's about 10. Now, g of 1. We've got to find the inner function, which is g of 1. Go to 1, go up to g, and we have y value of 3. So this is like g of 3. Go to 3, go up to g, I have a y value of 5. So this equals 5. F of minus 1, got to find the inner function, f of minus 1. So go to -1, go up to f, it's 5. So this becomes like f of 5. Now we go to 5, and we go up to f. And it looks to me, we can't actually see it, but it looks to me like if this was to keep going, probably something like -5, -6. Outside of the picture. Lastly, I could be real nasty and I could give you a whole bunch of nested questions like this. So this has f of g of 0. It doesn't make it any harder, but it makes it more steps. So we've got to work inside out. G of 0 first. Go to 0, go up to g, and it's 2. So this is like f of g of 2. Now we go to g of 2. Go to 2, go up to g, and it's a 4. So g of 2, like 4. So this is f of 4. Go to 4, f of 4 is 0, which is convenient. So this is f of 0. And at 0, f of x is 8. The next question is exactly the same, except instead of a graph, we have to find our values in a table. We're still searching for y values of specific functions. So f of 3, for example, we would go to 3. 3 is our x value, that's our input. F of x is -2 when x is 3. So f of 3 is -2. G of f of 3 is like g of -2, because f of 3 is -2. Go to -2. G of -2 is 12. Next one, f of g of 3. G of 3 is 4. So this is f of 4. F of 4, go down to 4, is 9. G of 4, so we go to 4, figure out what g is. At 4, g is 2. So this is like g of 2. G of 2, go to 2, is 0. F of 2. F of 2 is 0. So this is like f of 0. At 0, f is -6. F of g of 4, go to g of 4. So go to 4, g of 4 is 2. This is like f of 2. F of 2 is 0. now f times g of 1. This goes back to what we did yesterday. We have to build f of g of x first. This is like f of 1 times g of 1. Now, at 1, f is 9, so f of 1 is 9. And at 1, g is minus 5, so g of 1 is minus 5. So this boils down to 9 times minus 5. That equals negative 45. All right, last thing in the notes today. And you can expect to see a problem like this in your unit assignment. This is another strategy for finding inverses. So remember f inverse of x, the inverse of f of x, what we did to find it was we swap x and y, then solve for y. So we're going to do that with two functions, and we're going to see what happens when we try to find the inverse. So f of x equals 4x plus 3. So we need to find f inverse. We need to switch x and we need to switch y. So instead of y equals 4x plus 3, we can write this as x equals 4y plus 3. Got to solve for y, so we need to move our 3. X minus 3 equals 4y. And then we need to divide by 4. X minus 3 over 4 equals y. So now we've figured out the inverse, or f inverse of x. So we're going to do something a little different here. We're going to take the inverse and use it as an input for f of x. So we're going to go f of f inverse of x. We're going to replace x with its inverse everywhere in f of x. So f of x used to be 4x plus 3, so this is like 4 bracket plus 3. And in those brackets, we're going to write f inverse, which is x minus 3 over 4. Do a bit of simplifying. The 4 being multiplied and the 4 in our denominator can be canceled. This equals x minus 3 plus 3, which equals x. We're going to now work the other direction and go f inverse of f of x. So f inverse of x was x minus 3 over 4. So I'm going to write bracket minus 3 over 4. And in the brackets, I'm going to write f of x, which was 4x plus 3. We've got to simplify this. So 4x plus 3 minus 3 over 4. Our 3's will cancel, and we'll be left with 4x over 4, or x. Both of these equaled x. And that's the thing you need to check for. So we didn't really prove it, but we've kind of come up with a new strategy to test for inverses. So the two functions f of x and g of x are inverses if f of g of x equals g of f of x, which equals x. So in order to check for inverses, you need to find f of g of x. You need to find g of f of x. If both of them work out to x, you know g of x and f of x are inverses of one another. It's kind of a roundabout way of testing, but it is an alternative to swapping x and y, because sometimes you can't actually solve for y. And that is it. So we talked about what a composite function is today. A composite function is where you replace x with another function in f of x, or whatever your function is called. We built some composite functions. We then worked backwards where we were given a composite and we had to find the originals, f and g. To do that, we looked for patterns. After that, we were given graphs or tables instead of functions, and we needed to use those to find f of g of a specific value, like g of f of 7 or f of g of 2. And then lastly, we've developed a new test for inverses by finding f of g and g of f of x. So that's where I'm going to end the notes now. I've got some problems for you, page 307, 4, and then 6 to 10. That's going to be your homework for today. I'll end the video now, so take care, everyone, and I will see you all in the Zoom session tomorrow.